So, good day to all of you. So, we are already on our first chapter for CPT 221 operating system. So, chapter 1 is entitled Introduction. So, the slides that I'll be using for this presentation and the next presentations is not owned by me, but of course, it is officially from the operating system concepts book that I am using by Silbers, Galvin, and Gagne. So let's start chapter 1. So I hope that your brain cells are all ready so that you can absorb all the operating system concepts that I'll be discussing for chapter 1. So again, let's start. So chapter 1 introduction content. So we have what operating systems do. We have computer system organization. We have computer system architecture, operating system operations, resource management, security and protection, virtualization, distributed systems, kernel data structures, computing environments, free or libre and open source operating systems. These are the objectives of Chapter 1. Describe the general organization of a computer system and the role of interrupts. Describe the components in a modern, multiprocessor computer system. Illustrate the transition from user mode to kernel mode. Discuss how operating systems are used in various computing environments. Provide examples of free and open source operating systems. So first is we have the computer system structure. So computer system can be divided into four components, namely hardware, operating system, application programs, and users. So first component is the hardware. It provides basic computing resources. So these resources are the CPU, memory, and I/O devices. And then for the operating system, this controls and coordinates use of hardware among various applications and users. So if you're going to correlate operating system is like a manager. If an OS is a person. And then another component, of course, is the application programs. Define the ways in which the system resources are used to solve the computing problems of the users. So application programs ranges from word processors, compilers, web browsers, database systems, and video games. So for word processors such as Microsoft Word, Google Docs, so that's an example of a word processor. And then compilers, of course, these are included in the IDE of a programming language. And then, of course, the web browsers such as Mozilla Firefox, Microsoft Edge, Google Chrome. So these are examples of web browsers. Then for database systems, so we have SQL, Microsoft Access. And then, of course, there are also video games that can be installed. So it's also an application program. So actually in modern day or in the Metro version, these are now called apps. And the next is we have the users. So users are typical the people. It can also be machines or other computers if there are no human intervention. So it's not just people. It's just very commonly for people to be users, but machines or other computers can also be users if there is no human intervention with the operation. Okay, so the abstract view of components of a computer. So this is the illustration. So the user actually, it's not really interacting with the operating system unless the user is a programmer. But then a typical programmer is interacting with application programs installed inside the operating system. So it is already said that application programs compose of compilers, web browsers, development kits, and others. And then these application programs are installed inside the operating system. And then this operating system, this controls the computer hardware resources, the CPU, memory, I/O devices, and this computer resources will be managing by the operating system in which resources will be given to a particular application program that needs, for example, a CPU, memory, I/O devices, and others. So again, operating system acts like a manager of the whole computer system. So what operating systems do? So actually it depends on the point of view. So for users, their expectation for the operating systems is that users want convenience. There are no hassles, there are no problems. And then ease of use. It should be easily learned. The interface is for them, it's intuitive. And then it should have a good performance, meaning they should not expect there should be no system crash, system failure. So for them, that's good performance. Actually, users don't care about resource utilization, because as long as users felt that the usage of the operating system is convenient for them it is used easily and it's very inefficient. They don't really care what happens in the background. So actually, utilization is a background process. But shared computers such as mainframe or mini computer must keep all users happy. What is this? Of course, why keep all users happy? Because by using mainframe or mini computer, there is a setup that in which that if there are 100 users connecting to the mainframe or mini computer, they should not encounter any issues or problems while simultaneously connecting to this shared computers. So meaning even there are concurrent or simultaneous users of the system, they should not experience any issues or concerns. So operating system is a resource allocator and control program, making efficient use of hardware and managing execution of user programs. So I've said again, if an operating system is a person, he or she is like a manager. So users of dedicated systems such as workstations have dedicated resources, but frequently use shared resources from servers. So workstation, they have their own CPU, they have their own memory, they also have their own application programs in which they can process the data. But what is the use of the servers? The use of the servers is the data that they're processed, they're going to save it in the server so that the other workstation can access the updated data or the information in the database. And the next, mobile devices like smartphones and tablets are resource poor. Why they are resource poor? Because they're optimized for usability, ease of use of the user, and battery life, to prolong battery life. So mobile user interfaces, of course, for smartphones, they're already using touch screens, and there is also a feature for other smartphones which has voice recognition. Some computers have little or no user interface, such as embedded computers in devices and automobiles. So actually class, any digital device, it has an operating system and it also has a central processing unit. Okay, so for this example, there are computers that have no lil or no user interface, such as for automobiles. For automobiles, specifically the automatic transmission automobiles, they are using computer box for that. So what is that computer box? For manual transmission of automobiles, to shift from one gear to another, you have to shift gears. While in automatic transmission, the shifting of gears depends upon the speed of the vehicle. So the computer box is the ones computing when to shift to another gear, and of course when the person will hit the brakes, it will automatically again adjust the gear depending on the speed of the vehicle. So there is no user interface for that. So those computers with have little or no user interface, they run primarily without user intervention. So next is we have defining operating systems. So term OS covers many roles. Because of the myriad designs and uses of OS, present in toasters, as I've said, operating system is not just Windows 10, it's not just Linux. They can also be found in digital devices, as already stated here, in oven toaster, in microwave ovens, through ships, spacecraft, game machines, the one that you can find in malls, televisions, okay, not the CRT or the cathode ray tube, the fat one, but of course your LED or smart TVs or Android TVs, and industrial control system. So you already have a subject of programmable logic controller or control. So that is also, there is also an operating system there. So OS born when fixed use of computers for military became more general purpose and needed resource management and program control. So what is an operating system? So actually, there is no universally accepted definition for the operating system. So, quote unquote, everything a vendor ships when you order an operating system is a good approximation. But because operating system has different features, it varies wildly. So another definition, the one program running at all times on the computer is the kernel. Okay, the definition of the kernel is the one program running at all times on the computer. Okay, kernel, it's not the food, not the kernel corn. It's just the term kernel. It is a part of the operating system that runs at all times on the computer. And then everything else is either a system program, ships with the operating system but not part of the kernel. So, an example of a system program is the registry editor, or an application program, all programs not associated with the operating system, or these are the third-party software that you have installed inside your computer that has a purpose, for example, for word processing, for gaming. So that is an application program. So today's OSs for general purpose and mobile computing also include middleware. So what is a middleware? It is a set of software frameworks that provide additional services to application developers such as databases, multimedia, and graphics. So middleware are very commonly used in databases, multimedia, and graphics. So next is we have computer system organization. So the computer system operation, so we have an illustration here. So one or more CPUs, for this example, we have only one. Device controllers connect through common bus providing access to shared memory. So as you can see, for this illustration or diagram, we have one CPU, one disk controller that manages the disks. We have USB controller that manages any devices that connects through the USB port. And then we have also the graphics adapter, in which of course the monitor is connected. And then these devices are connected in the common bus or called the system bus, and they're also they share the resources in memory. So concurrent execution of CPUs and devices competing for memory cycles. So that is why they need the memory resource. So it's up to the operating system of how to manage or how to give a chunk of memory for this devices connected in the system bus. Okay, next is we have computer system operation. So I/O devices and the CPU can execute concurrently. So I/O means input-output devices. And then we have the CPU. Okay, again, let's correct the notion. CPU, again, it is the central processing unit. It is also called the processor or the microprocessor. But it should never be the notion of that the CPU is the casing in which the motherboards and other internal computer parts are there. It's not a CPU, but rather it is a system unit. So each device controller is in charge of a particular device type. As you can see in the illustration, this controller, of course, manages the disks. And then each device controller has a local buffer. And then each device controller type has an operating system device driver to manage it. So what is this device driver? So device driver acts like an ID of a device. How does this work? Example, you have a USB flash drive that you're going to connect to the computer for the first time. If you're going to connect it, you can see that there is in the lower right hand corner that it says that the device driver for USB is installing. So what is the purpose of installing? So that meaning if you can imagine the interaction between the computer and the flash drive, it goes like this. For example, the USB drive is connected. It's like the USB flash drive present his or her ID by means of the device manager by installing it. And then the computer, so you are a USB flash drive, so I will give you the proper resources that a USB flash drive have. So, after installing, and then the computer already recognizes that it is a USB flash drive, so the next time that it will be connected, it does not need to install anymore its device driver because it is already installed and the computer already know the identity of the device that has connected. Okay, in relation to flash drives, okay, so have you ever encountered, for example, you bought a flash drive, for example, the capacity is 4 gig. Okay, sorry for the handwriting. Okay, 4 gig. But when you see the actual size of the flash drive, we have 3.5, just as an example, okay. It's not totally 4 gig. So the question now is, where is the missing 500 MB? Where is it? Did the manufacturer of the USB lied? That why did you market it as 4 gig but the actual size is 3.5? Where is the 500 MB? Okay, the 500 MB, the reason why it's missing, it's not really exact, 4 gig, 8 gig, or 16. It's because the missing drive is already reserved for the device driver. It is where the device driver, the installation for the device driver is located. So even if you reformat your flash drive, it will always fall as not exactly as 4 gig because that space is already dedicated to the device driver, of course, of the device. So that's why they're not really lying or they did not scam you. No, it's because again, the device driver is installed inside the flash drive. Okay, another importance of device driver, for example, you have a specialized device such as a drawing tablet. Unless you have an internet connection in which the computer can search the drivers online, but what if you do not have it, standalone computer, and then you just have a specialized tablet, and then you do not have the proper device driver for it? The problem is that the computer may misallocate the resources needed by your drawing tablet. Example, you connected your drawing tablet which is connected through USB port. Since it does not have a proper device driver, it may recognize the device as a keyboard or a touchpad. So that's why what will be the problem? The features of your device will not be maximized or will be misconfigured because it is recognized as a touchpad or as a keyboard. So again, to maximize the performance of your device, you should have the device driver for the computer to, so you are drawing tablet, so these are the resources that you need, so that the computer, or rather the operating system, can properly allocate resources for that particular device. So that's why, again, device driver is very important. So let's continue. CPU moves data from to main memory to from local buffers. I/O is from the device to local buffer of controller. So device controller informs CPU that it has finished its operation by causing an interrupt. So what is an interrupt? So in the next slide, I'm going to discuss to you, is it the same interrupt that is happening in our daily lives, or is it different for the operating system? So common functions of interrupts. So interrupt transfers control to the interrupt service routine generally through the interrupt vector, which contains the addresses of all the service routines. Interrupt architecture must save the address of the interrupted instruction. So a trap or exception is a software-generated interrupt caused either by an error or a user request. It does not necessarily mean that if there's an interrupt, there is already an error. It can be also that it is a user request. And then an operating system is interrupt driven. So we have an example here of an illustration of an interrupt timeline. So For the interrupts, these are the types of interrupts. We have IO request, transfer done, interrupt signaled, interrupt handled, and it will be repeated depending on the request. So the CPU has user program running, and then there's also the process of IO interrupt processing. And then the IO device is, the state is idle or transferring. So this line means, if it is, the line is in here, meaning the user program is executed by the CPU. And then if the line is down here, so it means that the CPU is processing the IO interrupt. So that is the state. It's just, they cannot be processed at the same time. It's just one at a time. And then for IO device, of course, it's also the same way with the CPU. If it is idle, it is idle status, and then if it is in transferring status, so this will be the line. Okay. So to further understand this interrupt timeline, let's have a real world analogy for it. Example, CPU is the mother, and then IO device is a child. For example, the user program executed by the CPU, for example, is the mother is cooking. So the mother is cooking to this line. And then we have an interrupt request. The child says, Mommy, I'm going to the restroom. I'm going to have solid unload. I'm going to poo-poo. Okay. So what did the mother say? Okay, go ahead. But did the mother stop cooking? No. She continues to cook. Okay, so of course, the child has already went to the restroom. So this is unloading while the mother is still cooking. And then, after the child has already finished unloading in the restroom, okay, the term really is unloading, okay, then the child shouts, Mommy, I'm already finished with my unloading. Will you help me wash? Okay, then the mother said, okay, please wait a while, but still cooking. And then at some point, the mother stops cooking, and then next is the IO interrupt processing. Um, she helps the washing of her child's, that. And then after washing, and then the child has already finished in the restroom, and then again the mother continues to cook, and then after that, the IO device or the child is idle, and then what if there is another need? So that's again another request. So this cycle always repeats, and then the length of the transferring, it depends upon the data. So why did I give an example of a mother and a child? So that you can picture out that the interrupt that is happening in the operating system is just like what happens in our real life. That, for example, again, another example is you're doing something, and then a person asks you something, and then he immediately needs an answer. So if you're doing something, for example, in your computer, you're typing, you have to remember, oh, I'm going to stop here so that if I return, I can continue my work. You answer the question of the person, and then you go back to work. So that's already the interrupt. An interrupt that is happening in the real world is also the same with interrupts happening in the operating system. Okay, next is we have computer startup. So bootstrap program is loaded at power up or reboot. So this is typically stored in ROM or read-only memory or EEPROM or erasable programmable read-only memory, generally known as firmware. Okay, so we have this firmware. So firmware, it is very important. So firmware must not be corrupted, because if it is corrupted, then you will have a problem with the usage of your computer, or your computer will not be usable anymore. It's very important. So there are cases, for example, in laptops or PCs that are connected in the computer, that there is a request for firmware update. Actually, it's better to update the firmware, but you have to be very careful while updating the firmware, because number one, if you're going to read the instructions for updating the firmware, these are the two conditions for the laptops. Number one is the battery should be full. And then number two, it must be, the AC power must be connected to the laptop. So why? So that in case of power interruption, the battery is still fully charged and it will continue installation. You cannot, the firmware installation must be completed, because if not, the problem will be, it will affect the bootstrap program, and it will not load the OS at all. Or I don't know if newer computers has this feature that, for example, the firmware did not updated completely, then it will revert back. So it's better. But if this is the older computers, you really have to make sure that it has enough power supply and make sure there will be no power interruption. So actually for desktop PC it's more difficult because they don't have battery packs, unlike laptops. So bootstrap program, so again, very important because it initializes all aspects of the system. And of course, it loads operating system kernel and start execution. So though operating system is installed in our computer, it's not always in the memory. Okay, so for it to be loaded into the memory, especially its kernel, bootstrap program should load the operating system kernel. It will not load itself in the memory. Okay, next is we have interrupt handling. The operating system preserves the state of the CPU by storing registers in the program counter. As I've said, for interrupt handling, um, the the operating system preserve the states of the CPU by storing registers in the program counters. But in real life situation, we're going to remember where did I end, and then I will entertain the question of the person who approached me, and then after that, he or she is already satisfied, I'm going to return to my work. Okay, determines which type of interrupt has occurred. So we have two types. We have the polling and vectored interrupt system. For the polling, an I/O loop in which an I/O thread continuously reads status information waiting for I/O to complete. So that's the definition of polling. And another one is the vectored interrupt system. The purpose of the vectored interrupt system is to reduce the need for a single interrupt handler to search all possible sources of interrupts to determine which needs service. So separate segments of code determine what action should be taken for each type of interrupt. So we have here an illustration of CPU and I/O controller, and how does interrupt happens between these two hardware resources. So first for the CPU, number one, device driver initiates I/O. Then next, it's its I/O controller's function initiates I/O. And then number three, input ready, output complete, or error generates interrupt signal. As you can see, while the I/O controller does the initiates I/O and this third step, what is CPU doing? Is the CPU idle? No. What is it doing? So the CPU executing checks for interrupts between instructions. So aside that the I/O has its own function, the CPU looks for other interrupts. So after this step number 3, and then it goes here. So CPU receiving interrupt transfers control to the interrupt handler. Then next, interrupt handler processes data, returns from interrupt, and then next, CPU resumes processing of the interrupted task. So, and if there is a I/O request again, the cycle repeats. So that is how the relationship of the CPU and I/O controller in terms if there is an interrupt, or how does these two handle interrupts. Okay, next. Next is I/O structure. After I/O starts, control returns to user program only upon I/O completion. So what will happen to this first condition? Wait instruction idles the CPU until the next interrupt. There is a wait loop, contention for memory access. At most, one I/O request is outstanding at a time. No I/O, no simultaneous I/O processing. So it means that I/O request is done one at a time. There is no multitasking for I/O processing. And then there's another scenario. After I/O starts, control returns to user program without waiting for I/O completion. So for this one, we have the system call. So system call is request to the OS to allow user to wait for I/O completion. We also have the device status table, contains entry for each I/O device indicating its type, address, and state. And then OS indexes into I/O device table to determine device status and to modify table entry to include interrupt. So that is the two types of I/O structure. Okay, next is we have the storage structure. So we have main memory and secondary storage. Okay, for main memory, only large storage media that the CPU can access directly, as you can see in the diagram, with the CPU, disk controller, USB controller, and graphics adapter. So the characteristics of main memory is it is random access. So meaning, if you put your data in sequence, it does not mean it can access in sequence too. No, it's a random access. So it's relatively faster. And then it's typically volatile. So what is the meaning of volatile? So volatile is a property of liquid that liquids has a tendency to evaporate. So that is volatile, or the noun is volatility. So that's why if you can recall your high school in which your science teacher discussed, or your father or mother reminded, or your grandparents reminded you that do not let the bottle of the alcohol uh, uh, lid is open, because the alcohol evaporates faster than water. So that's why. That's the volatility, the property of a liquid to evaporate. Okay, so volatile is associated in science in liquid. So why does main memory as the characteristic of volatile? Is it a liquid? Of course not, because main memory is a chip. So how will you relate volatility in main memory? Volatility in terms of um, data that is stored in main memory. So meaning, if the main memory loses power, the data that is stored in main memory will evaporate, or it will not be retained. So, what is the evidence of the main memory's volatility in terms of data storage? Example, you have a slideshow presentation using your desktop PC. Then suddenly, there is a power interruption. And then when the power is restored, and then you turned on the computer, what happens? So your desktop PC, it's either returns to the usual routine of booting, or of course, since there is a power interaction, there is a premature shutdown of your computer. So it will have a notification, or a reminder that the Windows does not run, it's not properly shut down. So you have a selection of start Windows normally. So then again, if there's no problem, then, and if you're going to continue the presentation, you have to open again the presentation um, file. So that's the scenario. So where does the volatility there? If the main memory is not volatile, when there is a power interruption, and then when the power is restored and you turned on your computer, the last slide of the PowerPoint, or the slideshow file should be still loaded in main memory. So by that, meaning because of power interruption, the data that is stored in the main memory is also lost. So you need to reopen it again. And as you can already guess or infer, that all programs that are running or that we are using it's always loaded in memory. And then if you do not use anymore the program, it will be its instance will be removed from the main memory so that other programs can use that memory space. Again, typically random access memory in the form of dynamic random access memory, DRAM. So dynamic, we also have another one, the static. So dynamic, it has something to do with the capacitance of the main memory. That, as I've said, because it's a main memory and it's volatile, if the power is cut or there is no power flow for the main memory, then there will be the data will be lost. So for the dynamics, the capacitance of storing electricity for the main memory. Okay, next is we have secondary storage. Extension of main memory that provides large non-volatile storage capacity. So secondary storage, so hard disk drives, HDD, and non-volatile memory, NVM, falls in the secondary storage. So HDD, rigid metal or glass platters covered with magnetic recording material. So the disk surface is logically divided into tracks, which are subdivided into sectors. And then the disk controller determines the logical interaction between the device and the computer, specifically that devices the disks, rather. And then the next is we have the non-volatile memory or the NVM devices. So these are faster than hard disk, non-volatile. So actually, NVM, this is now what you know as the SSD, okay, or the flash drive. Actually, the technology of the flash drive comes from, rather, of the SSD comes from flash drives. Okay. Okay. Sorry for the handwriting. Okay. Flash drives. Because unlike hard disk drive that uses rigid or glass platters, SSD uses chips. So it is faster because it does not, unlike hard disk drive, to read is the glass platters turn and there is a read arm. There is a read arm for it. For SSD, it acts like a flash drive. So of course, since this is faster, so it's expensive. So there are various technologies and brands for SSD. So various technologies are the SSDs and flash drives, thumb drives. And it's becoming more popular as capacity and performance increases and price drops. For flash drives, so compared 10 years ago, um, the flash drives are very expensive, but nowadays it's not anymore. And then for SSD, so actually again, when it's earlier release, it's very expensive, but still it's relatively expensive than the hard drives. Example, a 500 gig SSD costs almost 3,000, in which for that 3,000, you could already have a 1 or 2 terabyte hard disk drive. Okay, storage definitions and notation review. So the basic unit of computer storage is the bit. A bit can contain one of two values, 0 and 1. All other storage in a computer is based on collection of bits. Given enough bits, it is amazing how many things a computer can represent. Numbers, letters, images, movies, sounds, documents, and programs, to name a few. A byte is 8 bits, and on most computers, it is the smallest convenient chunk of storage. For example, most computers don't have an instruction to move a bit, but do have one to move a byte. A less common term is word, which is a given computer architecture's native unit of data. A word is made up of one or more bytes. For example, a computer that has a 64-bit registers and 64-bit memory addressing typically has 64-bit or 8-byte words. A computer executes many operations in its native word size rather than a byte at a time. So, computer storage, along with most computer throughput, is generally measured and manipulated in bytes and collections of bytes. A kilobyte or KB is 1024 bytes. A megabyte or MB is 1024 raised to 2 bytes. A gigabyte or GB is 1024 raised to 3 bytes. And a terabyte or TB is 1024 raised to 4 bytes. And a petabyte or PB is 1024 raised to 5 bytes. Computer manufacturers often round off these numbers and say that a megabyte is 1 million bytes, but it's not really, it's just really a round off. It's not the actual or the exact number of bytes. And a gigabit is 1 billion bytes. Networking measurements are an exception to this general rule. They're given in bits because networks move data a bit at a time. So next is we have storage hierarchy. So storage systems are organized in hierarchy and it depends upon the speed, cost, and volatility. So we have the term caching, copying information into faster storage system. Main memory can be viewed as a cache for secondary storage. Device driver, as already discussed, for each device controller to manage I/O, perform uniform interface between controller and kernel. So this is the illustration of our storage device hierarchy. So we have storage capacity and access time. So of course, for storage capacity, the one at the top, it has a smallest capacity, while at that bottommost part, it has the largest capacity. But for the access time, of course, the smaller, the faster access time, and the larger, the slower the access time. It's like, for example, if you're looking for an item, for example, if you know that you've lost your item in your room, it's easy to find because of the space. You can easily locate it. Compared it that you lost an item, you don't know really where exactly it is, but you know that it is lost inside your house. So what are you going to do? You're going to look for every corner of your house. So it's more time consuming than an item lost in a small room. So that's also the notion or the correlation between the storage capacity and access time. Okay, so the smallest, of course, is are the registers, and then followed by the cache. Actually, registers and cache are located inside the CPU or the microprocessor. And then we have main memory. So this three, the registers, cache, and main memory, these are called the primary storage, and there are the volatile storage, meaning if the power is lost, then the data will also be lost. And then next is we have non-volatile memory and hard disk drive. So these are called secondary storage. So after main memory, these are already classified as non-volatile storage. And then lastly, we have the optical disk and magnetic tapes, and these are the tertiary storage. So the hierarchy works this way. If magnetic tapes, if the register has an updated data and wants to update the magnetic tape, it will not directly go to the magnetic tape, but rather it will go to the data will go to the cache, main memory, non-volatile memory, hard disk drive, optical disk, and magnetic tapes. Why? So that the data will be updated and all of them are all updated. So that's the purpose of the storage device hierarchy. So also when the magnetic tapes has a data and the register is requesting for it, so it will go through the optical disk, the hard disk drive, non-volatile, main memory, cache, and then it will go to the register. There is no direct connection between the registers or the magnetic tapes because of the access time. So it will consume a lot more time. So this is very optimal for access time. Okay, how a modern computer works. So we have a CPU, a device, and then memory. Inside the CPU is we have a thread of execution, and inside the CPU, of course, as I've said, there is a cache. Then in memory, so we have instructions and data. There is a bidirectional for instruction execution cycle. And then there's a data movement between the CPU and the memory. And then this device, when the CPU wants a I/O request from the device, And then there's also a movement between the CPU and the device for the data. And then if a device wants to have a service, it will issue an interrupt to the CPU. But at the same time, the device can have a DMA or direct memory access to the memory itself. So this setup is called a von Neumann architecture. So it's not von Neumann but von Neumann. As a correction, German. So I've already mentioned DMA or direct memory access. So it's a structure. It is used for high-speed I/O devices that able to transmit information at close to memory speed. It is allowed. So DMA is allowed if the I/O device is high speed, that it's able to transmit information at close to memory speed. Okay, not all devices can have DMA. Only those devices that are high speed, that is close to memory speed. Then device controller transfer blocks of data from buffer storage directly to main memory without CPU intervention. And then only one interrupt is generated per block rather than the one interrupt per byte. Okay, next is we have computer system architecture. So most systems use a single general purpose processor, meaning in your computer system, you only have one physical processor. Example, typical computers are always physically one or a single processor. General purpose processors, these are considered the processors of the computer because it can perform many tasks. But most systems have special purpose processors as well, such as processor for microwave oven, for the automobile, for the digital clock. So there's purposes for, of course, microwave oven, for the automobile, for the clock, for the game console. So that these are called the special purpose processors. So if we have a single or physically one processor, we also have this setup which are called multiprocessor systems. So multiprocessor systems growing in use and importance because the system unit can house two or more multiprocessor depending on your motherboard. So also known as parallel systems or tightly coupled systems. So the advantages of multiprocessors are increased throughput. So what is throughput? Generally, the amount of work done over time. Of course, if multiprocessor can be compared to two intelligent persons, the work will be finished easier if it is done by two people than one person, unless these two are arguing, and of course the other is um, um, working in solo. If they cannot agree on something, of course this one will be finished. But of course, there is a saying that two heads are better than one. And then next is economy of scale. Of course, it depends upon your motherboard. And then increased reliability, graceful degradation or fault tolerance, meaning if your processor 1 crashes, the processor 2 can take over the jobs of processor 1 without any system failure. That's why there is a fault tolerance. Okay, we have two types of multiprocessing. We have asymmetric multiprocessing. Each processor is assigned a specific task. And then symmetric multiprocessing, each processor performs all tasks. So this is an example of a setup for asymmetric multiprocessing architecture. So we have two physical processors. They have CPU sub-0 and CPU 1. And then they have the same sets of registers and cache. And then they are sharing just one main memory. So that's why they can perform all tasks because these are all loaded in one memory. They have shared main memory. Okay, next is we have a dual core design. So this is also called as a multi-chip or multi-core. So dual core means two cores. But now Because of technology, there is octa-core. So 8 cores meaning. So systems containing all chips, so chassis containing multiple separate system. Okay, what's the difference between a multiprocessor and a multi-core? The difference is that for multiprocessor, if you have two processor, there are physically two processors. But for this example, for the dual core, physically there is only one processor, but inside the processor is we have two CPU cores, which they have their sets of registers and L1 cache, and they share L2 cache inside the processor. And again, we have the main memory. So, meaning if it is an octa-core, if you're going to open the device, you can only find one physical CPU, but inside it, we have 8 cores. It's like for person, it's like this. If you're a person and you are a dual core, meaning inside your skull or inside your head, you have two brains. That's the meaning of that, of the dual core, multi-core. So it's an octa-core, meaning inside your head, you have 8 brains. Wow. I hope that it's really very intelligent. Okay, next is we have the non-uniform memory access system or NUMA system. So the NUMA system is we have different CPUs, so in a system unit. So they have their own sets of memory. These are not shared, while this CPU are interconnected with each other. So that's the meaning of non-uniform memory access system. Okay, next is we have clustered systems. So like multiprocessor systems, but multiple systems working together. So multiprocessor is like two processors or more inside a system unit. These clustered systems are multiple computer systems that are working together. So usually sharing storage via storage area network or SAN. And then next is provide a high availability service which survives failures because of course clustered systems are working together as one. So we have this asymmetric clustering has one machine in hot standby mode. So meaning, the one who does all the work is the computer one. When the computer one crashes, computer two will take over. So that is the one machine in hot standby mode. Hot standby just in case that, again in the example, computer one has crashed. And then next is we have the symmetric clustering has multiple nodes running applications monitoring each other. So some clusters are for high performance computing. So applications must be written to use parallelization. And then some also have distributed lock manager to avoid conflicting operations. So this is an illustration of the clustered system. So in this example, we have 3 computers that are interconnected to each other. And then they have this storage area network that they shared with each other, or the SAN. Okay, next is we have PC motherboard. As you can see, I think you're already familiar with the motherboard. So consider the desktop PC motherboard with the processor socket shown below. So this is the processor socket, this is for the DRAM, and this is for the PCI bus slots and various I/O and power connectors. This board is a fully functioning computer once its slots are populated. It consists of a processor socket containing a CPU, DRAM sockets, PCIe bus slots, and I/O connectors of various types. Even the lowest cost general purpose CPU contains multiple cores. Some motherboards contain multiple processor sockets, so that's why multiprocessing system depends on the motherboard if it can accommodate two or more processors physically. More advanced computers allow more than one system board, creating NUMA systems or the non-uniform memory access system. Okay, next is we have operating system operations. So you've already discussed previous the bootstrap program, the simple code to initialize the system, and that loads the kernel. And then after the kernel loads, and then after loading the kernel, it starts with the system daemons, so which are the services provided outside of the kernel. And then kernel is also an interrupt driven. It can be hardware or software. And then hardware interrupt by one of the devices. So software interrupt may be exception or trap. So for software interrupt, it can be an error, such as division by zero, of course. So division by zero in mathematics is undefined because you cannot divide anything by nothing. And then next is request for operating system service, or what we call the system call. Other process problems include infinite loop, processes modifying each other, or the operating system. Okay, next is we have multiprogramming and multitasking. So for multiprogramming or batch system, so needed for efficiency. So multiprogramming means you're giving commands to a computer in which commands are entered into files and the files are executed without any human interaction. And then batch system is done in groups. Okay. So single user cannot keep CPU and I/O devices busy at all times. So multiprogramming organizes jobs, code, and data. So CPU always has one to execute. And then a subset of total jobs in system is kept in memory. So one job is selected and run via job scheduling. So we're going to study later on what is this job scheduling and how is it done. When it has to wait for I/O, for example, OS switches to another job. Then we have time sharing or multitasking. It is a logical extension in which a CPU switches jobs so frequently that users can interact with each job while it is running, creating interactive computing. So response time should be less than 1 second because if the response time is greater than 1 second, the user can notice that it's not really multitasking, but it's just swapping from one job to another. So each user has at least one program executing in memory. So a program that is loaded or executing in memory, it is called a process. If several jobs ready to run at the same time, so we'll be having CPU scheduling. So we're going to study how CPU scheduling is done and how it works. So if processes don't fit in memory, swapping moves them in and out to run. So that is what I'm saying earlier. And then virtual memory allows execution of processes not completely in memory. So virtual meaning it's not really a memory. It's not really the main memory. Again, there's also a separate discussion for what is virtual memory. So memory layout for multi-program system. So this is the memory. So of course, as I've said, that the operating system must already have its allocated memory space inside the main memory, and then depending upon of how many processes or how many programs are open. For this example, there are 4 programs that are open, so that's why there are 4 processes inside main memory. Okay, next is we have the dual mode and multi-mode operation. So dual mode operation allows OS to protect itself and other system components. So this dual mode is, we have the user mode and kernel mode. So mode bit provided by hardware provides ability to distinguish when system is running user code or kernel code. Some instructions designated as privilege only executable in kernel mode. System call changes mode to kernel, return from call resets it to user. So increasingly, CPU support multi-mode operations such as the virtual machine manager mode for guest virtual machines. So how does the user mode and kernel mode work? So this is an illustration transition from user to kernel mode. So timer to prevent infinite loop or process hogging resources. So timer is set to interrupt the computer after some time period. Keep a counter that is decremented by the physical clock. Operating system set the counter or privilege instruction. Then when counter 0 generate an interrupt, then set up before scheduling process to regain control or terminate program that exits allotted time. Okay, so we have an illustration here. So how can we easily understand this? So imagine again a scenario. You're going to save a file. You're typing your document. Then you want to save a file. So the process or the time that you are typing, you are in user mode because you're interacting with the application program with your word processor. So that's why for the user process executing. Okay, you're typing. So that's the user process executing. So you want to save your file. So for example, your file is very big that when it saves, it takes relatively a long time. So you want to save. So you're going to click the save. So that is when the time the operating system has the call system call. Okay, call system call. So when it's saving the file, so I've said the scenario is you have a big file. So can you imagine, is there a typical or an experience, for example, if you're loading a very big file, the cursor is buffering. So actually that time that the cursor is buffering, meaning that is the time that it is in kernel mode. So that's why, for example, so again, you are typing and then you want to save a very big file. So when the cursor is buffering or going in circles, meaning it is already in the kernel mode, saving your file. So execute the system call which is saving your file. So the trap mode bit is equal to 0 because you're already in the kernel mode. Because user mode bit is equal to 1. So, and there is a timer for this one. Timer. Why? Because that the kernel mode must not be very long, because what will happen is the user will be um well, it's not bored. Why does it took too long to save? Is there any problem? Is there an error? So that will be the mindset of the user. So as much as possible, kernel mode time must be fast so that the user will not think that it has an error, the application program has hanged. So that's it. So for example, if it will successfully save your file, your very big file, then it will return mode bit is equal to 1 and return from system call, and then you can type again your document. So that is the from transitioning user to kernel mode. So what will happen if, example, the system call stays too long in the kernel mode? As you can see, there is a message, for example, for the application program not responding, and then not responding, and then there is already a dialog box saying that Microsoft Word is not responding. Would you like to wait for the program to respond? Um, Close it. Okay, so we have these choices. So that is that happens when the system call took too long in the kernel mode. Okay, again for user and kernel mode. So user mode is the user is interacting with the application program, while in the kernel mode, this should took a very short time so that the user cannot will not think that the application has hung or there is an error. So that is the user mode to kernel mode and vice versa. Okay, next is we have process management. So a process is a program in execution. So once your application program that is installed in your computer is loaded in memory, meaning it is already a process. It is a unit of work within the system. So program is a passive entity, meaning any application programs that you have installed but haven't run, it is a program, while process is an active entity such as this one. So I am using a slideshow presentation software. So meaning the slideshow presentation software is an active entity because it is loaded in memory. While my word processor is a program because at this time I'm not using a word processor. So you can differentiate the program and process. So process needs resources to accomplish its tasks. such as what are these resources? We have CPU, memory, I/O, and files. And then we also should have initialization data. So process termination requires reclaim of any reusable resources. So that's why, for example, if I close this slideshow presentation, any resources such as CPU, memory space, I/O, or files, specifically memory, it should free up space when I'm already finished with this slideshow presentation. And then single-threaded process has one program counter specifying location of next instruction to execute. So process execute instructions sequentially one at a time until completion. So multi-threaded process has one program counter per thread. So we have the single-threaded process and multi-threaded process. Then typically system has many processes, some user, some operating system running concurrently on one or more CPUs. Concurrency by multiplexing the CPUs among the processes or threads. So, what are the process management activities? So, the operating system is responsible for the following activities in connection with process management. So, we have creating and deleting both user and system processes, suspending and resuming processes, providing mechanisms for process synchronization, providing mechanisms for process communication, and providing mechanisms for deadlock handling. And then next is we have memory management. To execute a program, all or part of the instructions must be in memory. All or part of the data that is needed by the program must also be in memory. So memory management determines what is in memory and when. So optimizing CPU utilization and computer response to users. So what are the typical memory management activities? So keeping track of which parts of memory are currently being used and by whom, deciding which processes or parts thereof and data to move into and out of memory, and allocating and deallocating memory space as needed. So next is another is we have the file system management. So OS provides uniform logical view of information storage. So abstracts physical properties into a to logical storage unit, which is a file. Last, in relation to file, for example, you have a video file. We can see that in the folder as a single file, the video file. For example, a 2 gig video file. We can see that as a single video file, but actually when it's stored in the hard drive, well, let me show you a hard drive. If you're going to store it in the hard drive, that video file can be stored in here. It can, okay, hard drive. Okay, it can be stored here. It can be stored there, where, here, and everywhere. So, meaning, that file is just an abstraction that we as user can only see that as a single file, but in reality, it can be stored in different tracks and sectors in the hard disk drive. So that's why you can notice that if you're going to open a video file that you have saved a long time ago and you haven't done the so-called defragmentation, okay, okay, sorry again for the handwriting because of course I'm a left-handed and the mouse is of course is oriented as right-handed. Okay, defragmentation. Sorry. Okay. Okay, defragmentation. If you haven't done defragmentation, if you're going to load your 2 gig video file, again, it depends upon your processor. But then, if you're going to load your whole video file for your hard drive, it will locate all the files and then it will load it into memory. So that's why it is lower because as you can see, in reality, the bigger files are stored in separate files. But if you will do the fragmentation, these separate files will be, since they are the parts of the same file, they will be compressed and they will be on the same location so that the loading of that video file is easier. So each medium is controlled by a device such as a disk drive or tape drive. So varying properties include access speed, capacity, data transfer rate, or access method, may it be sequential or random. So file system management, files usually organized into directories, then access control on most systems to determine who can access what. Then the OS activities include creating and deleting files and directories, primitives to manipulate files and directories, mapping files onto secondary storage, and then backup files onto stable or non-volatile storage media. Okay, next is we have mass storage management. Usually, disks used to store data that does not fit in main memory or data that must be kept for a long period of time. So mass storage, these are non-volatile because even there is no power, the data is still stored there. And then proper management is of central importance. As I've said that proper management, you should conduct the fragmentation at least monthly. And then entire speeds of computer operation hinges on disk subsystem and its algorithms. What are the OS activities for mass storage management? We have mounting and unmounting, free space management, storage allocation, disk scheduling, partitioning, protection. And then some storage need not to be fast, such as the tertiary storage includes optical storage and magnetic tape, but it still must be managed by OS or applications. Okay, next is we have caching. So caching is already an important principle performed at many levels in a computer in hardware operating system or software. Information in use copied from slower to faster storage temporarily. Then faster storage or cache, check first to determine if information is there. If it is, information used directly from the cache, which is fast. If not, data copied to cache and used there. So cache smaller than storage being cached. So cache management, important design problem, and then cache size and replacement policy. So we have the characteristics of various types of storage, as I've said. So registers are the smallest. So as we can see, one less than 1 kilobyte. So the largest, of course, is magnetic disk, less than 10 terabyte. So this is the hierarchy: registers, cache, main memory, solid state disk, and magnetic disk. And then implementation technology. So for registers is custom memory with multiple port CMOS. For cache is on-chip or off-chip CMOS SRAM. For main memory is also CMOS SRAM. For solid state disk is flash memory, which is used by flash drives. And then magnetic disk, of course, is magnetic disk. Or this is actually magnetic disk. This is the hard disk drive. So access time is in nanosecond, NS, nanosecond. So fastest is the registers, and of course, the slowest is the magnetic disk. Then bandwidth, so megabytes, because capital M and capital B, so megabytes per second. So registers has a bigger bandwidth compared to magnetic disk. And then register is managed by the compiler, cache is managed by the hardware, main memory is managed by the operating system, the SSD and magnetic disk is also managed by the operating system. So registers is backed up by cache, so cache is backed up by main memory, so main memory is backed up by disk, solid state disk is backed up by disk, or magnetic disk is also backed by disk or tape. As you can see, the ones that will back up this register is the next level, the one beside it. So movement between levels of storage hierarchy can be explicit or implicit. So migration of data A from disk to register. So multitasking environments must be careful to use most recent value no matter where it is stored in the storage hierarchy. So for example, the hardware register needs a data from magnetic disk. So it will go to the cache for the request to the main memory and then magnetic disk, and the magnetic disk will send the needed data to the main memory. So the main memory will have a copy, then it will be passed to cache so that the cache will also have the copy, and then the register will have the copy. So it means they have all copies and they are all coherent. So multiprocessor environment must provide cache coherency in hardware such that all CPUs have the most recent value in their cache. So distributed environment situation even more complex. So several copies of datum can exist and various solutions covered in chapter 19. Okay, let's go back with this storage. As you can see with the storage hierarchy, so I have this real world analogy for our storage. Okay, so that's why we have this one. For example, let's do this, the hierarchy. So imagine that the table, the desk, of course, this is the register, and then the in-out file is the cache. And then, for example, you have the drawer here, which is the main memory. Okay, main memory. Okay. And then, the solid state disk, for example, is this cabinet, SSD. And then we have another magnetic disk, another cabinet farther. So we have magnetic disk. So migrating data, for example, um, the register needs the register needs data. Or of course, for example, you as a person needs data. Would you search directly to the magnetic disk? No. As a person, would check first your desk if there is the data. Example, that's the register. So, oh, the data's not here. Then you're going to look for the cache. It's not yet here also. Then you're going to look in the drawer, which is the main memory. Oh, it's not also here. Then, if you're going to look at the SSD, oh, it's not also here. So, maybe it's really in the magnetic disk. So, that is how the migration of data works. It will always start on the smallest. And then, if you have found the data, so the only difference in the real world is that it will not create a copy for the SSD, for the main memory, for the cache to the register, is that the data from the magnetic disk will be brought to the register. So that when you're already finished, and then you're going to think, is it going to be used again or not? So if you have the gut feeling that the data will be used again, then it will stay on your desk for the register. Okay? So that is how the storage hierarchy works for getting the data. But for searching for data, it's just the same with the hierarchy, that it looks first to the smallest, and then to the next, and then to the next. But for the moving of data, compared with the next example, that it will copy an instance for the main memory, for the cache, and then for the hardware register, no. But for a real world situation, once that you've found that the data is in here, it will be directly copied here. So it is not applicable here because there will be there is a cache coherency that this illustration follows. Okay, next is we have I/O subsystem. So one purpose of OS is to hide peculiarities of hardware devices from the user, of course, because the user, again, only wants convenience, ease of use, and good performance. They don't care if I have a specialized device, the computer should recognize it as long as it has a proper device driver. So the I/O subsystem is responsible for memory management of I/O, including buffering or storing data temporarily while it is being transferred, caching, storing parts of data in faster storage for performance, spooling, the overlapping of output of one job with input of other jobs. And then we have general device driver interface. This general device driver interface is for example, um, a long time ago, if you have a mouse and it is branded, for example, it is branded Logitech, it has a specific driver for Logitech mouse. But nowadays, disregarding of the brand, since it is a mouse, it is always identified by the computer as a mouse without even the brand anymore. So that is the general device driver interface. And then drivers for specific hardware devices, I've already discussed. What if you have specific hardware device such as a drawing tablet? So you should have a specific device driver for that to maximize the features of your hardware device and as not to misidentify by the computer or the operating system that the drawing tablet will be a trackpad, touchpad, or a keyboard, worst case. Okay, next is we have protection and security. So protection, it is any mechanism for controlling access of processes or users to resources defined by the OS. Then security, defense of the system against internal and external attacks. So protection is more of having a username and password for authorized access. So that's already a protection. So for security, it's more of viruses, malware. So for security, huge range, including denial of service, worms, viruses, identity theft, theft of service. So systems generally first distinguish among users to determine who can do what. So user identities such as user ID, security IDs include name and associated number one per user. So for the computer, if you have your name as your user ID, so we have its name and associated number. Then user ID then associated with all files, processes of that user to determine access control. For example, if you're the administration or the administrator, you can install, uninstall a software. So that is the admin rights. Then we also have group identifier or group ID, allows set of users to be defined and controls managed, then also associated with each process or file. So, an example of group identifier in Windows is we have everyone. Everyone is like a guest. You can view, but you cannot install or uninstall programs in a computer. And then we have privilege escalation, allows user to change the effective ID with more rights. Example, if you're a guest, but if you know the username and password, then you will have a privilege escalation from guest to administrator. Okay, next is we have virtualization. So, allows operating systems to run applications within other OSs. So, it is a vast and growing industry. So, emulation used when source CPU type different from target type such as PowerPC to Intel x86. So, generally slowest method when computer language not compiled to native code, so it is interpretation. So, virtualization, OS natively compiled for CPU running guest OSs, also natively compiled. So, consider VMware running Windows XP guest, each running applications all on native XP host OS. And then VMM or Virtual Machine Manager provides virtualization services. So emulation is different from virtualization because again, the source CPU type is different from the target type. And then for virtualization, the OS is natively compiled for CPU running guest OSs also natively compiled. So mostly emulation is used for games. For example, you have a soft ISO file for your uh, PlayStation portable game, and then you want it to run it to your PC. So that's an example of emulation. So I have an example here that can show the uh, the emulation. Okay, so we have example. Let's open a folder. Okay, let's wait. Okay, so I already have this in the recent. So we have this PPSSPP. Actually, this is a PlayStation portable emulator. Okay, so we've already opened. So I have this recent game. So let's example. This is an example. This is actually a file, an ISO file. So this ISO file actually works with the actual, of course, customized or modified PlayStation Portable because the original PlayStation Portable uses UMD discs. They are not using ISO file, but if it is modified or modded, it means that it is modded. They can use ISO file. So this ISO file here is actually played. Okay, this is played, can be played in PlayStation Portable, but because I have an emulator for PSP, which is the PPSSPP, so I can also play the ISO file here. So this is an example of an emulation, meaning again, for emulation, the ISO file is intended for PlayStation Portable, but because they created a software that covers, that hides the details that the CPU and the graphics controller is actually of of a general purpose computer or a general purpose processor, which is from the PC. So that's why the file thought that it's really running a uh, in a PlayStation Portable game console. So that is an example of emulator. I have emulators more here. Actually, the ones that we've done when you were first year, the last game that you've played, it's also an emulator of an arcade game. But it's already an old, so I think you did not encounter that anymore. So that's an example of an emulation. So, for virtualization, this is one of your projects. You're going to install an operating system using a virtual machine manager. And I'll just give you maybe next week the list of OSs, and whatever group number you are, then that is the OS that you're going to install in a virtual machine manager. So let's continue our discussion. So, use cases involve laptops and desktops running multiple OSs for exploration or compatibility. Actually, there's no problem if you're going to run multiple OSs in virtualization as long as the host OS has still enough resources for CPU and memory. Because if you will assign CPU core and memory to the guest OS that is not enough anymore for the host OS, then there will be a problem for loading. So you have to make sure that the host OS has still enough resources for it to manage the guest OSs. So the examples of virtualization, so Apple laptop running Mac OS X host Windows as a guest, that's possible. Developing apps for multiple OSs without having multiple systems. Other multiple systems such as dual boot. So what is the difference of dual boot and virtualization? For dual boot, when you're going to boot the PC, you're going to select if you want to load Windows 10 or Linux-based operating system. You cannot load them both. It's exclusively, if you choose Windows, then it's Windows. Then if it's Linux, it's Linux. So for virtualization, you can run two or more OSs at the same time, depending upon the resources available. So that is an example. An Apple laptop or vice versa, we have a Windows 10 running, and then in the virtual machine, you have a Mac OS 10 running. So QA testing applications without having multiple systems. That is also the purpose of virtualization. And then executing and managing compute environments within data centers. So VMM can run natively, in which case they're also the host. There is no general purpose host then for VMware ESX and Citrix Xen server. So for virtualization, so this happens if there are no virtual machine managers. So we have the hardware and then the kernel and then the processes. But if you have a virtual machine manager, for example, VirtualBox or VMware, and for this example, you have this the host OS, and then it runs 3 OSs at the same time, simultaneously. Again, there is no problem with this setup as long as the host operating system has enough resources such as CPU and memory to run these other three virtual or guest OSs, because these three OSs still needs CPU and memory. Okay, so this is an example of virtualization. That imagine virtualization is that operating system is just like another application program that you can still do anything, even this virtual this guest OS is running. You can imagine it as like that. Okay, next is we have distributed systems. So we have distributed computing. So it is a collection of separate, possibly heterogeneous systems networked together. So network is a communications path. TCP/IP is the most common. So we have these types of networks. We have the local area network, or LAN. So LAN is example network in a computer laboratory. So that's an example of a local area network. So wide area network is, of course, networks between, for example, your house and the the other of your one of your relatives. It's a wide area network. So, or another is, for example, wide area network is considered as our enrollment system. We are when it's not yet online, our database is centralized in the main campus. So that's also an example of wide area network. So metropolitan area network, of course, it's mostly in the cities. Actually, here in the Philippines, it's not yet really that implemented, because metropolitan area network spans the whole city. For example, for an internet connection, there is one common internet connection for the whole city that is free. So that is already an example of a metropolitan area network. And then we have this personal area network. So your phone connected to your smartwatch. So, or your Bluetooth headset connected to your phone. So that is already an example of a personal area network. So next is we have network operating system, or NOS, provides features between system system across network. So communication scheme allows system to exchange messages. So it is an illusion of a single system. So next is we have the kernel data structures. So many similar to standard programming data structures. So for kernel data structure, we have three. We have singly linked list. So linked list means we have a portion for data and a portion for a pointer, and this pointer next to the connects to the next uh, element, which is again contains data and a pointer. So that is the singly linked list. What is a doubly linked list? It's also a singly linked list. It's just that they have three partitions for data, and then two for the point. We have one for the pointer, but the middle also acts as a pointer. So it's like circular. It's just that they have two pointers going to and going back. And then we also have circular linked list. It's like a singly linked list. It's just that the last data will be pointing to the first element. So that's why it's a circular linked list. Okay, we also have a binary search tree. So we have this rule that left is less than or equal to right. So as you can see, 17 is the number. So it means that all that is located on the left side of 17 are less than 17. So we have 12, 6, and 14. And then any number greater than 17 is on the right side. So 35, 32, and 40. I will have a separate lesson here on how to construct binary search tree from a pre-ordered list. of elements. So search performance is big theta function of n. That's the big theta notation. So balanced binary search tree is big theta function of log n. So if it is big theta function of n, so running time is linear, while big theta function of log n, running time grows at most proportional to log n. So that is the performance or running time for searching the binary search tree. Don't be concerned about the search performance or the balance search tree. For this lesson, separate lesson, I'm going to teach you how to create a binary search tree. Okay, so hash function can create a hash map. So hash function takes data as its input, performs a numeric operation on the data, and returns a numeric value. And then a hash map, which associate key value pairs using a hash function. So bitmap is a string of n binary digits representing the status of n items. So Linux data structures defined and include files such as linux/list.h, kfifo.h, and rb3.h. Okay, next is we have computing environments, the traditional ones. So the traditional is considered the standalone general purpose machine. Standalone meaning they are not connected to any network or internet, but blurred as most systems interconnect with others, such as I said in the internet. So the standalone, strictly, these are not connected to a network. So portals provide web access to internal system, and then network computers such as thin clients. So we have this thin and not thick clients, okay? Fat clients. Thin clients means they only have CPU and memory, but the processing of data is done in the server. While the fat client means they have CPU and memory and storage such as hard drive that when the application program is stored in the client, um, but the storage of data will be shared in the server. So that is the fat client. So network computers, thin clients are like web terminals. So mobile computers interconnect via wireless networks. Of course, specifically your smartphones. You do not have an interface anymore for a network cable, but it's always with Wi-Fi. And the networking becoming ubiquitous. Even home systems use firewalls to protect home computers from internet attacks. So networking ubiquitous meaning it is everywhere. So that's the meaning of ubiquitous. Okay, for what about for mobile, the computing environments? So these are handheld smartphones, tablets, and others. So what is the functional difference between them and a traditional laptop? So for mobile, so mobile is more of the smartphones, and then the traditional laptop is, of course, you can still do many things in a laptop than in a phone. And of course, not all apps are still there's still apps in the smartphones that are still questionable. And then we have also have extra feature, so more OS features for mobile, such as GPS, the global positioning system. So that's why you can use Google Maps. So that's actually very helpful for travelers as long as you have data that you don't need to ask persons where is it. By means of GPS, you can already travel, specifically if you have Google Maps. And then what is this gyroscope? So gyroscope is also a feature of smartphones in which, for example, you're playing a racing game, and then if you tilt it on the right, the car will turn right, or if you're going to tilt it to the left, then it will turn left. And then it allows new types of apps like augmented reality. So the first device that I've seen with augmented reality is Nintendo 3DS. But because of Pokemon Go, there is already an augmented reality, but it's not as impressive as the teaser because I thought for the teaser, it's like the the Pokemon is already existing, it's just invisible. But if you're going to play it in a game, I don't know because it's already a long time ago. I haven't played Pokemon Go. I don't know if the augmented reality has already improved. So the next is we have the use of IEEE 802.11 wireless. So that's the code for wireless network, the IEEE 802.11 wireless devices. That's the name. So, or code name, name that is used by IEEE. Or cellular data networks for connectivity. So leaders for mobile are Apple iOS and Google Android for the operating systems. Okay, what is the computing environments for client server? So we have client server computing. So dumb terminals supplanted by smart PCs. So we have many systems are now servers responding to requests generated by clients. So we have a compute server system provides an interface to client to request services such as database. And we also have a file server system provides interface for clients to store and retrieve files. So compute server system is used for request services, while file server system is to store and retrieve files. So this is an example of a setup diagram for the client server. So we have client, disregarding if it is a desktop, laptop, or smartphone, they're connected to a network and they're connected through a server. And then the network is wireless. It's not anymore wired. Okay, next is we have peer-to-peer. So another model of distributed system. So P2P does not distinguish clients and servers. So that's why it's called peer-to-peer. All the computers that are connected in a P2P network, they are all equal. So instead, all nodes are considered peers. May each act as a client, server, or both. So node must join P2P network, registers its service with central lookup service on network, or broadcast requests for service and respond to requests for service via the discovery protocol. So examples include Napster and Nutella, voice over IP or VoIP such as Skype. Another example that uses the peer-to-peer is that if you're familiar with downloading torrents. For downloading torrents, we have this seeders and we have the term seeders and leechers. So seeders, these are the nodes or computers that has the complete copy the of the file that you are downloading, while the leechers, of course, that's why it's called leech. You're only downloading, but you're not uploading. So you're just having that's why it's called leechers. So for the health of a torrent file, if there are many seeders, it means many computers that are connected in the P2P network have that copy. But if the seeders is already 0 and then you want to download, you may still download the file, but the problem is there is a possibility that you can't complete the download because there is no computer that has a complete file for that. So for downloading torrent files and of course they're using P2P, you have to make sure that the health of the torrent file is still high, which means it has a high number of seeders. So seeders are only considered seeders if the computer that has downloaded the file has already completed downloading and they have a number of days in which they will upload the file, or how many days that they are online, so that the other users can still download the file. But I hope for downloading, of course, the torrent files is because you've got it for free, at least be a seeder so that they all can benefit. So these are examples of the P2P. So actually this Napster actually is a music sharing service. But it has become but it's already rebooted. It has been closed because of the P2P network downloading music files, and then it was being charged by the music industry in the US because of piracy. So that's why now Napster now is sharing files with a fee, because the last time that they did that, it's for free. And of course, we can understand that if we get music files for free, we're not really supporting the artist. So that's why if you really are a fan of a music band, of a boy band group, um, please patronize them by buying their original albums to help the music industry. So that's why I'm just telling a story about the Napster. Okay, next. So how about cloud computing? The computing environment for it is delivers computing, storage, even apps as a service across a network. So logical extension of virtualization because it uses virtualization as the base for its functionality. We have Amazon EC2, or EC2 means Elastic Compute Cloud, double C, so that's why it has two at the end. Amazon EC2 has thousands of servers, millions of virtual machines, petabytes of storage available across the internet, pay based on usage. So we have many types. We have the public cloud, available via internet to anyone willing to pay. They also have the private cloud, run by a company for the company's own use. Hybrid cloud includes both public and private cloud components. And then we have software as a service, or SaaS, one or more applications available via the internet such as word processor. Actually, Google Docs is already an example of software as a service. For example, Adobe Photoshop Express, in which you can edit, tweak your images. Um, you don't need to download the Adobe Photoshop or buy the software, install it in the computer. You can already edit your image using Adobe Photoshop Express online. So that those are example of software as a service. Next is we have platform as a service, or PaaS, software stack ready for application use via the internet, such as the database server. And then we have another one, structure as a service, or IaaS, servers or storage available over the internet. They can be storage available for backup use. Actually, software as a service is more popular because these are used by consumers. Unlike platform as a service and infrastructure as a service, these are more are available in the companies, or bigger companies usage. Okay, for continuation for cloud computing. So cloud computing environments composed of traditional OSs plus VMMs plus cloud management tools. So internet connectivity requires security like firewalls, of course, for intrusion detection. And then load balancers spread traffic across multiple applications. So we have the internet, of course, you should have a firewall for accessing to protect intrusion. And then for customer requests, so cloud customer interface, and then the cloud management commands, and then it will go through the cloud management services. And then for the traffic, we have to control the traffic. We have the load balancer so that the virtual machines and storage and cloud management services will have the needed traffic that they need from the internet. Okay, for real-time embedded systems. So real-time embedded systems, most prevalent form of computers, vary considerably. Special purpose, limited purpose OS, real-time OS. So use are expanding. So example of a real-time OS is the medical equipment that is used in the hospital. For example, for displaying the heart rate. So it should be real time because, knock on wood, if the person is already dead, it should be shown in the monitor that there is no heartbeat anymore. So the medical equipment is faulty, that the person is already dead, but there's still an indication that he or she is still alive. So that's why it's very important for the medical equipment to have a real-time OS. And then many other special computing environments as well. So some have OSs, some perform tasks without an OS. And then real-time OS has well-defined fixed time constraints, as I've said, for medical equipment. Processing must be done within constraint and correct operation only if constraints are met. So next, last but not the least, is we have free and open source operating system. So operating systems made available in source code format rather than just binary, closed source, and proprietary. So this free and rather open source. What's the difference between free and open source? Free software meaning you can download the software for free, but you cannot modify its source code. Okay? While open source, you can download the software, install the software for free, but at the same time, if you want to modify it, and for example of open source operating systems such as Linux, if you want it to change and create your own operating system, you can change it if you know how to modify the source code of the Linux operating system. So actually, Windows is a closed source and proprietary because, for example, for newer computers, Windows 10 is already included in the package of buying a laptop. But you cannot modify Windows 10 unless, again, you are a very good programmer, you understand the programming concepts in operating systems. So it is counter the free and open source operating systems are counter to the copy protection and digital rights or DRM movement. So this open source operating system is started by Free Software Foundation (FSF), which is copyleft. So actually copyright. So they are the copyleft. GNU Public License or GPL. Free software and open source software are two different ideas championed by different groups of people. Again, as I've said, free software, you can download it for free, but you cannot modify its source code. While open source software, you can download the file, the software, but at the same time, if you want to change the feature or add additional features for that particular software, you may do so by changing its source code. So this is the site for the GNU public license. So open source misses the point. So an article. So examples include GNU or Linux and BSD Unix, including core of Mac OS X and many more. So can use VMM like VMware Player. So this is the virtualization software that you can use, the VMware Player, which is free on Windows. VirtualBox, open source and free on many platforms. So this is another virtualization software that you can use for installing the OS. So used to run guest operating systems for exploration. So the study of operating systems. So there has never been a more interesting time to study operating system, and it has never been easier. The open source movement has overtaken operating systems, causing many of them to be made available in both source and binary or executable format. The list of operating systems available in both formats include Unix. Actually, that's BUSD Unix or BSD Unix, Solaris, and part of Mac OS. The availability of source code allows us to study operating systems from the inside out. Questions that we could once answer only by looking at the documentation or the behavior of an operating system, we can now answer by examining the code itself. So that is the advantage of getting the source code of the operating system, because we can be educated of how does this operating system works, how does it behave for a certain issues or problems. Then operating systems that are no longer commercially viable have been open source as well, enabling us to study how systems operated in a time of fewer CPU, memory, and storage resources. An extensive but incomplete list of open source operating systems project is available from this link. In addition, the rise of virtualization as a mainstream and frequently free computer function makes it possible to run many operating systems on top of one core system. For example, VMware provides a free player for Windows on which hundreds of free virtual appliances can run. VirtualBox provides a free open source virtual machine manager on many operating systems. Using such tools, students can try out hundreds of operating systems without dedicated hardware. So that is actually the advantage of using virtualization software. You do not need to buy specific hardware for you to run that particular OS. So the advent of open source operating system has also made it easier to make the move from student to operating system developer. With some knowledge, some effort, and an internet connection, a student can even create a new operating system distribution. As I've said, if you really know how to program, how to modify the source code of operating system, you can create an operating system with your own name on it. Just a few years ago, it was difficult or impossible to get access to source code. Now, such access is limited only by how much interest, time, and disk space a student has. So again, so as I've already said that the limits of your imagination, it's just you're in your limits, but in the internet you can already find sources that is educational for you to use. It's not just used for watching K-pop or K-dramas or any other entertainment. I hope that you will use your resources for education also. So this is the end for chapter 1. So I hope that you're still okay. So I hope that by means of my real world correlation or real world scenario, you can already understand some of the operating system concepts. So rest assured that I'll always do that. Those technical terms, I can explain it in a layman's term or correlate it in a real world analogy so that you can further understand its concepts. So if you do have any questions, so please feel free to comment below, and hope you don't forget to like my page. So again, so see you on the next chapter, chapter 2 of our subject CPT 221 operating system. So thank you very much and good day.